Welcome everyone. We're very happy to see so many people at our science seminars. And today we are very happy and honored to welcome Dr. Naftali Tishbi from Hebrew University of Jerusalem. He's one of the leaders in machine learning and computational neuroscience in Israel. He pioneered several applications of information theory and statistical physics to computational learning theory. Recently, he introduced some new theoretical frameworks for optimal adaptation and efficient information representation in biology, such as the Information Bottleneck method and the minimum information principle for neural coding method. And also, he developed a very intriguing way to analyze deep neural networks with information theory. And one of his recent talks was watched on YouTube more than 30,000 times. And he was very kind to come here and present the extended version of this talk. So thank you very much.
Good evening. Do you hear me? All right. It's really a pleasure to be here in Moscow. It's the first time for me in Russia, and so far I'm very impressed. I'm one day here, and I'm very impressed by the everything. So it's especially such a young crowd. So I know that this talk is being recorded and actually broadcast live, which is kind of annoying because, as you just heard, I mean, my last Yandex recorded talk hit over 34,000 viewers today, if I'm not wrong, which is completely mind-boggling. It's changed, in some sense, the impact of my work in a way that no paper or conference or journal paper could. So maybe science is advanced these days, or in very different ways, like talks like this, and which are recorded and can be viewed many, many times. So I know that I guess many of you haven't watched this talk, but so when I was invited to come here, I was happy, of course, but I thought, okay, I already talked about deep learning. Maybe I should talk about other things here. And then over the last 2 months since this talk was put on YouTube, I got so many interesting questions about my talk that I realized that maybe I should take this opportunity and expand and clarify many of the things that I very quickly went through in this half an hour talk, which was extended to 50 minutes, but it was still a half an hour talk. So here I assume that I have more than an hour, and not all of you are probably experts in everything, so I'm going to go slowly at first, but then there are many more technical details which I'm going to skip tonight, but maybe elaborate more on Friday on the other talk that I have here. So deep learning, as you all know, is now the most important not only machine learning device, but it's really changing the world in a way which nobody could expect. And so this is a very successful story that starts with the story of neural networks in general. And as you all know, I mean, neural networks are brain-inspired in some sense. I mean, people are trying to mimic the way neurons interact in the brain, but the relation with biology is weak at the best at this point. I mean, it's essentially based on this notion of the McCulloch-Pitts neuron, which was invented and introduced already in the 40s, which essentially tried to capture what we call the essence of the neuron. So a neuron is a special cell that connects to many other cells in strengths or synaptic efficacies which are varying and adaptive. And essentially, you can think about it as some sort of integrator of many, many pieces of information. It connects with other cells not because of any metabolic reason, but because it needs information. Essentially, it's an information processing device. And now we understand it very well. But in the 40s, I mean, this idea of having a neuron represented by just a dot product of some weights with inputs and then some sort of nonlinearity was very strange and very radical. But it took about 10 years until Frank Rosenblatt essentially suggested it as a pattern recognition device, which he called the perceptron. And indeed, so the birth of this story is really in the 40s. Perceptron, or Rosenblatt with his famous work in the 40s and 50s, already essentially envisioned the whole story. I mean, he was really thinking about many layers, but he invented one algorithm, which is known today as the perceptron algorithm, for essentially training only the last layer, or just what we call the linearly separable part of the problem. And then Minsky and Papert, during the 60s and early 70s, essentially with a very famous and beautiful book called Perceptrons, essentially very convincingly argued that this particular device is never going to work because linearly separable problems are very limited. So essentially the whole book is dedicated to this idea that the single layer perceptron cannot do anything interesting. And they also thought about, as Rosenblatt actually suggested, training many, many layers, but they said that this cannot be done. And in particular, this algorithm that we are all using now, stochastic or gradient descent through the layers, was considered by Minsky and Papert and was ruled out as unstable because they thought that it's going to get stuck in local minima or local optima very quickly. So this is actually a very ironic story because it postponed the interest in this type of machines until the 80s, maybe for the better, because by that time you already had computers which were strong enough to actually try this on real problems in some sense, much more than people could do in the 60s. And in this, during the 80s, the PDP people, Rumelhart, Hinton, and Williams, and others, essentially reinvented the perceptron with an additional twist, which was this very simple idea that you can actually train the deeper layers by propagating the derivatives of the error using the chain rule of derivatives. And eventually, this was really the beginning of what we now call neural networks for supervised learning like this. But again, in another interesting twist, this was taken out of the main stage by essentially the work of Vladimir Vapnik, who came from here. But in the late 80s, when he essentially was able to present his work in the States, actually I met him in 1989 during his first visit there, and he suddenly took us all by surprise by some very crisp theorems about what he called later on support vector machines and kernel machines, which really took over the community of what we now call neural networks. It was some sort of a twist at the two-layer neural networks, where the second layer was very wide and expanded it to very high dimension. And essentially, you could prove that using this trick, you can really linearly separable eventually a very complicated problem in a high dimension. But then, in the early 2003 to 2009, the same group of people who believed in neural networks, in particular Jeff Hinton and Jan LeCun and a few others, pushed this, of course, with the help of much stronger computers. And in around 2008, 2009, those reinvented or reincarnated connectionist machines, I mean the deep neural networks with many, many layers now, not just 2 or 3 or 5, but tens and hundreds, or even more, layers suddenly were manageable by a set of tweaks and tricks that didn't change anything in principle. But around 2008, 9, 10, those machines started to beat the state of the art in many, many different fields. In particular, computer vision, speech recognition, later on in control, in reinforcement learning, in playing Atari games, winning Go, and whatever you want. And eventually, I mean, it's completely revolutionized not only the field of signal processing and image processing, for example. I mean, many, many very elegant ideas that were developed by very clever people became essentially unneeded because those deep machines or deep neural networks beat them all in a very surprising, I must say, way. Okay, so as you can imagine, I mean, this is very bad news for theoreticians because we really realize that we don't understand what's going on. And we don't understand it on some very fundamental levels. First of all, we didn't understand oh, I'm sorry, I need to go back. We didn't understand, is this machine in some sense optimal? I mean, are deep neural networks the best we can do? Is there any bound that we know that can be achieved by these machines which we can compare them to deep neural networks in some sense? I mean, this is something we still don't know, but at least I believe we are beginning to have a clue about this. Do we have anything like design principles of these machines? I mean, do we know which architecture, what is the right number of layers or the right width of the layers for a given problem? I mean, how to design them? I mean, for any engineer, this is the first thing you want to know. I mean, you're given a problem, what should be the best machine for tackling it, for working on it? Of course, there was a big issue about interpretability. I mean, can we understand actually what these networks, what these layers, or these neurons, or neurons-like elements are actually doing, actually learning? I mean, what do they represent? I mean, in what sense this is a very good representation? Of course, there are many, many good ideas around, but the feeling is, still is, that we don't have a good theory of these things. Of course, nobody was terribly happy with the learning algorithms. I mean, stochastic gradient descent are in some sense very naive. I mean, that's the easiest thing you can do. We are used to much more sophisticated type of algorithms. Is there something special about stochastic gradient descent that we don't understand? Or is there something special, or maybe we can do much better, significantly better, by other algorithms? I mean, this is still, I believe, a wide open problem. And so essentially, what I'm going to tell you today is that over the last 5 or 4 years, we have developed, it may be a new theory to deep learning, but it's based on all the ideas that I've been pursuing together with many good people since the early 90s, at least, which has to do with the questions of relevance. I mean, what is it in a very complex signal that carried the relevant information about another signal? This was a fundamental question that I asked myself already in the 80s when I started to work on speech recognition, actually as a hobby. I mean, I was a physicist doing theoretical physics, but I thought that speech recognition is a cool problem. And I was at Bell Labs at the time, and I thought that the fundamental problem of speech recognition is really how to get rid of the irrelevant information, in some sense. Of all those, out of 100 bits per second that the speech signal actually carries, if you really want to preserve it accurately, only maybe 10 or 100 bits per second are really important for the contextual, for the actual content of the speech, for the speech recognition problem. So this is for me a very intriguing puzzle, and I went quite far into the foundation of this problem and invented, together with other people, something which we call the Information Bottleneck method or principle, which essentially addressed this particular question. How do you extract the relevant bits out of very complex signals in some principled way, principled and general way? Now, I started to think that this can be useful for deep learning already in the 80s, but then neural network became uninteresting for a lot of people, and the whole thing went into the drawer, and we used this information bottleneck for many other things. And then when actually under the cover of the Intel Collaborative Research Institute, the ICI, which you see on all my slides, this was actually supported by Intel in a very interesting collaboration with Intel and Academy in Israel, out of many centers like this that Intel had all over the world. And I was lucky enough to head this center for a while. So essentially, we developed this theory, and I must say that it was completely ignored at large until this talk in Berlin, I must say. So now it's becoming, it's under the examining the glass, the magnifying glass of a lot of people. So I'm sure that people will want to know exactly what happens. So essentially, we have, in this theory, we combine 3 different ingredients. And they are different in the sense that they require really different types of knowledge, and therefore there are not that many people who know all of them. So one of them is statistical learning theory. Statistical learning theory is the classical standard theory of machine learning, which was essentially started, or at least historically started, by the 1982 paper of Les Valiant, on which I'm sure you all heard of, that. It's called the theory of the learnable, where he invented what we call the PAC learning model. And the PAC learning model, probably approximately correct learning model, what was really beautiful about it is the fact that it gave us bounds on the generalization error, out of training error, in a very simple bounds, which were essentially distribution-free, distribution-independent, and very strikingly powerful, that essentially they express the number of examples needed for good generalization in terms of very few numbers, sometimes just one number, the dimensionality of the hypothesis class. Now, this is something which I'm sure anybody who learned about machine learning, took one course in theory of learning, heard about these bounds. Now, those PAC learning bounds, which I'm going to mention in slightly more detail in a second, turn out to be, as the worst case bounds in some sense, because they are completely distribution independent, and they turn out to be less and less useful when the problems became larger. And now we are talking, I mean, one of the things that really happened with deep learning in recent years is that the problems became really large. Really large in the sense that the inputs is now millions or hundreds of millions of random variables, like pixels of very high resolution images or videos or whatever you want. And for such large problems, essentially all those details of the PAC learning theory were not in the right place. I mean, for example, the confidence level that we were very careful to have in our PAC bounds, which is the probability of having the wrong sample, something which is not typical, is completely away, because now we are talking about very large samples. The probability of getting a non-typical or bad sample is completely negligible. On the other hand, those dimensions, like the VC dimensions or other thing, gave us way over pessimistic bounds. I mean, essentially, they don't describe the generalization ability of deep learning today at all. So the first ingredient of this theory was essentially to make a very big step backward. Let's look at distribution-dependent bounds in some sense, and I'll show you exactly in what sense, and try to make them more realistic by ignoring the hypothesis class altogether and going back to the properties of the data itself. Okay, so this is what I call PAC learning with a twist. And essentially, my main argument here is that we should go from what we call expressivity results. I mean, what is the power, the functions that those networks can express in terms of approximations, which are usually way too complicated for most we really need. And so we move from the hypothesis class to what I call the input compression bound. So this is the first thing I want to show you. The second ingredient of this getting or theory in incubation, in some sense, is information theory. Now, information theory usually is not studied by machine learning people. This is considered a theory of communication engineers. I mean, so this is a theory of data compression and of error correcting codes and all these things. But usually, of course, it is related to learning in many different ways that we know, but this was always considered marginal to learning theory. The reason I think that information theory is becoming very, very crucial now, it's not an information theory, by the way, it's all those large-scale theories like statistical mechanics and other things like this, which are essentially the same flavor as information theory, is that the size of the inputs, the size of the problem is becoming large enough to really consider typical images or typical patterns only. So in some very strict, precise sense that I will describe in a second, I restrict myself to typical problems or to typical inputs. So if I get a very distorted image of a face, no one is going to complain if I don't recognize the person there. I want to recognize the typical images, I want to recognize the typical voice, and typical is really what our brain is also good at. Okay, so this notion of typicality that happens with large-scale learning is another ingredient, very important ingredient of the story. And in some sense, it also shifts the issue of the optimality of the machine. I mean, in what sense we have an identifiable model? So we already know for a long time that those machine learning devices have many solutions which are very good. Those huge neural networks have infinitely many solutions which are very good. Essentially, they have exponentially in the size of the input, or actually even the size of the parameter space, different solutions which are as good. So in some sense, talking about the global minima of some error functions is a completely misleading picture. We're talking about very high dimensions and many, many possible configurations which can be very good or very close to optimal. Now, the third ingredient of this story is the dynamics of the training. So I'm going to argue the information theory alone cannot really, is not related, actually completely independent of the computational issues, which means how much time does it take to actually find a good solution. These are things which information theory ignores completely, and that's why information theory is not considered a very good theory for complexity, computational complexity. I'll show you why, and I'll show you why we need something else. But this something else is coming from a surprising place. In some sense, not surprising. We all know that the dynamics of the training, I mean, the stochastic gradient descent, has some very peculiar properties which somehow work together with the nature and the architecture of the machine, and somehow, in a way that I think is now becoming clearer, is giving us something quite surprising. So what I'm going to argue is that SGD, or stochastic gradient descent, in this very high dimension, actually has very different behaviors in two different phases of the training. At the beginning, what I call the memorization or the drift phase, it moves very, very quickly to in what we call memorization in some sense. We remember the data, and actually remember a lot of details about the data which are not important. And then most of the epochs of the stochastic gradient descent, or backpropagation, or whatever you call it, are actually spent on noise, on diffusion, on adding noise to the irrelevant components of the data. And it turns out that the way we do stochastic gradient descent using those mini batches in the training is actually very important, because this is precisely the origin of this noise in the gradient, which, as I argue today, is actually responsible for the good generalization. And because stochastic gradient descent is approximating eventually a Gibbs distribution or a maximum entropy distribution in the error, and that's something I'm again going to elaborate on, I know I can actually prove that in some very specific sense, this is pushing the layers of the deep neural networks to be optimal, information theoretically optimal, irrespective of any other machine in many interesting cases. Now, the last, or the bonus that we get from thinking about stochastic gradient descent as this diffusion process in the weight space that happens in the second phase of training is that we actually get a very nice and new explanation on the benefits of the many layers. Why do we need so many layers? Why do they help us so much? And it has to do with the convergence times of this stochastic gradient descent. Okay, so we get many results. I basically said it. We also get some interesting design principles, interesting interpretability results. We get understanding of the benefits of the layers, of the hidden layers, and we, as I said, get some sort of an optimality result on deep learning. Okay, so I already spent 40 minutes. I'm going to go very quickly through some of the slides that are on my Berlin talk. So essentially, the way we connect neural networks with information theory is by thinking about the layers as a Markov chain of representations. So essentially, remember this picture. X in this notation is the input data, which think about pixels of an image, for example. Many high-dimensional, many bits of random variables, which are, of course, correlated in a very complicated way. And y, in this case, is the label, which can be just one bit. Or, in the case of speech recognition, for example, is the word spoken in a certain utterance, a certain piece of speech. This is a much fewer bits than the number of bits required to describe the signal. So in most cases, and that's the cases I'm interested in, x is a high entropy variable, very complex variable, and y is a low entropy variable, very simple variable. And the secret of deep learning is this cascade of transformations from x to the first hidden layer, h1, or later on call it t1 or t2 and so on, and eventually at the end I get this approximate y, which I call y hat. Now, so because it's a Markov chain, there are all sorts of nice relationships we can say about information theoretic quantities which are related to this Markov chain. And again, I'm going to do it quickly because I'm sure many of you or most of our viewers certainly know these things. I'm going to need the notion of mutual information. So mutual information is, again, something which everybody knows of, but they usually think about it as some sort of an entropy-like function which measures correlation between variables, but actually a lot more than that. And those of you who know something about information theory, you know that mutual information is really the generator or the function which we maximize or minimize in the two main components of information theory, data compression or rate distortion theory in general, and source and channel coding or error correcting codes, which is the capacity in one case and the rate distortion function in the other case. So mutual information is a very important function. And so I hope you all know what the KL divergence is. It's essentially just, you see this arrow here? So essentially just the average log likelihood of two distributions with respect to one of them. It's a non-negative quantity, which is 0 only if they're equal almost everywhere. And the mutual information is the KL divergence between the joint distribution of two variables and the product of their marginal. And this is a non-negative quantity, again, which is 0 if and only if they're independent. But this function has two very peculiar or interesting properties. One of them is known as data processing inequality. It's a very intuitive thing. So if you move through a Markov chain, like the Markov chain of this network, data can only go down. Information can only go down. By the way, I get questions from it from a lot of people. Entropy, of course, can increase in the network. I can generate noise, or I can do all sorts of things, but I cannot increase the information about the input or the information about the output. So in this Markov chain that I described, the mutual information measures how much each layer remembers or knows about the input variable x, and how much it knows about the output the desired output variable y, and both of these things are going to decrease. The other thing which is quite important about mutual information, which actually is a special case of the data processing inequality, is that it's completely invariant to invertible transformations of the variables. Now, you think about this, this is precisely the reason why mutual information or information theoretic quantities in general are not very useful for complexity theory. Because, for example, if I take an image and I encrypt it with some very hard-to-break code through some very hard problem, computational problem, then, of course, the images will look like noise, like white noise or something like this. No deep learning algorithm can make sense of it unless it somehow breaks the code, breaks the encryption. And this can be as hard as I want. So information alone cannot tell us the whole story, and remember that. So again, this Markov chain representation, we have this decreasing chain of inequalities. The entropy is larger than the information within x in the first layer, and which is larger than the information within x in the second layer, and so on. And so it is about y. The maximum information that each layer can have about the label is bounded by the mutual information that the input itself has about the label. So I have these chains of inequalities, which in my language describe a line in the plan when I apply it to the hidden layers of the network. And this is what I want to call the information path of the layer, of the network at any given time. And of course, you should think about the hidden layers of a deep neural networks as some sort of partition of coarsening of the input. And again, if you actually think about the maps from the input to each of the layer as invertible, as a one-to-one function, as some people do, because actually, strictly speaking, when you use sigmoidal units or things like this, it is a one-to-one function, then no information is get lost at all. So there must be something in the process, in the way we think about the layers, which allow us to lose information, and that's exactly what I'm going to. So the quality, the properties of those partitions are really, very important, and they can't be one-to-one. You must think about it as some partition of the input into cells within which each layer is actually a different partition of the input, and since it's a Markov chain, they just coarsen the partition when I move from one layer to the next. Okay, so another way of thinking about it, which is very important for the main results that I'm going to show, is to think about every layer in the input as some sort of, every layer, the map from the input to the layer as the encoder of the layer. So this is some stochastic map in general, which tells me how the layer Ti in this case, is encoding the input, and the decoder is how the desired output Y, the label, is decoded from this input. So essentially, when you train the network, when you move through the layers, the complexity of the problems move from the decoder. So the first layer has a very complicated decoder, a very simple encoder. The second layer has slightly more complicated encoder and more complex decoder. And then when you move layer by layer, the decoder becomes simpler and the encoder becomes more complicated. And at the end, the last hidden layer, the decoder is very simple, essentially linearly separable. I can learn it with the perceptron algorithm if you want. But the encoder is very, very complicated. So my argument is that it is only the mutual information of those two functions, the encoder of the layer and the decoder of the layer, for the last hidden layer of the network, which really determines everything you want to know about the trade-off between sample complexity and accuracy of the network. So this is the fundamental theorem, I believe a fundamental theorem about deep learning, which has a lot of caveats and a lot of things to understand because it's not a very constructive theorem. But if I give you these two numbers, how much information there is in every one of the layers about the input and how much there is about the output, I'm actually telling you the whole story in terms of the trade-off between complexity and between sample complexity, number of samples you need, and accuracy, which is how well you do or what is the probability of error outside of that. Now, at this point, I like to show this movie, which I'm sure many of you saw already. So what you see here is what I call the information plane of the deep learning. So essentially, these are these two coordinates. How much information I have about the input versus how much information I have about the output. For every one of the layers, so we have 100 different repetitions of the same network exactly here. Very specific network. Small network, because otherwise we cannot estimate those quantities very well. And what you see are those different balls in different colors, or different circles in different colors. So this is the last hidden layer. This is the one before. This is, and so on. So there's altogether 6 hidden layers. Here is the input layer right here. You see it? Yeah. Okay. So, and what you see here are the initial conditions of this network. So essentially, at the initial conditions, the random weights are not doing anything very clever, and the information is essentially lost very quickly. And the last hidden layer at the beginning of the training has very little information, both about the input and the output. So now when you train the network, something quite interesting happens. I mean, first you see that all those layers come up, and then at some point, especially the last hidden layers start to move slowly. This is something which happens all the time. So it gets stuck at some point in the movie, but you see what I mean. So essentially, they move like this, and eventually, the last hidden layer moves to the left, and in some sense forgets a lot of the information about the input. So this is, I'm sorry about this technical issue, but I can show you those snapshots of the movie. So see, it gets to this point. This is an interesting point right here, where essentially all the layers lie on this decreasing line. So every one of these 100 repetitions is slightly different, but you see that they all converge in a very clear area in this information plane. So this is where the last hidden layers remembers the most about the input. And from this point on, the last hidden layer starts to move to the left and eventually forget many of the details of the inputs. And that's, at this point, the information about the output is as high as possible for all the layers, which means that I'm generalizing well, I'm fitting the data well. This information about Y is directly related to generalization error. And I'm also, all the layers and somehow move to the left. I forgot as much as possible from the lane. I want to show, if I show you, that's just the average of it. This is really this famous picture which was given in Quantum magazine recently. So essentially, this is just the average of the clouds that you saw before. So you see that up to very few number of epochs of training, you move to this point more or less. So you see those layers move essentially in one way, and then start this slow diffusion process, which is driven by noise in the gradients, as I'm going to show you in a second. And eventually, you get this convergence, very slow convergence, and each of those layers is moving to a different place along a very special line in this plan, and which I'm going to argue is the optimal line for this rule. And you see that I keep on moving, and through this convergence of the layers, the last hidden layer is slightly losing information, but is still gaining information by the movement to the left of the hidden layer. So the compression actually helps you in generalization, and eventually you converge to this nice picture. So remember this, the last hidden layer is doing something very quickly, moving here, and then slowly moving to the left. And I argue this is a very typical behavior. You see it in many different problems. I don't want to spend too much time here about the role of stochasticity, but there's something very peculiar about the mapping that I'm doing now between deep neural networks and the information bottleneck. And one of them is that it turns out to be essential that the rule that you are learning is not completely deterministic. And this sounds very strange to a lot of people, because usually we have very clear labels. This is you, and this is not you, and so on. But in fact, when we talk about such large problems, very similar pictures have different labels, and essentially it acts like a noisy rule. Now I argue, and this is one of the consequences of the theory, that this is indeed noisy. And actually, the way we measure mutual information, so in these pictures that I just show you in these movies, mutual information is measured by binning the neurons in the hidden layers into levels, essentially finite number of bins. This is one way of taking this continuous one-to-one function and essentially turn it into a lossy function by essentially binning the layers into number of cells. Some people are not happy with this binning because it seems arbitrary, so we actually tried a lot of other ways of binning it, and essentially this turns out to be quite robust, and no matter how you do it, we actually checked 3 different ways of doing it. One is binning the variables, the other one is adding noise. You can add noise to the layers themselves. A lot of people are thinking about stochastic neurons, and then of course, when you add noise, you make it lossy or you lose information. But this is not what actually happens in deep learning. Those algorithms are not stochastic in general. That's why I didn't like it. And the other way of measuring mutual information is by using some sort of parametric models. For example, approximated the joint distribution by a mixture of Gaussians, or doing something like this. This is a trick, very effective trick actually, to estimate information. All of them give you very similar results, and in all of them you see this picture, that the layers move first to the right very quickly and then slowly to the left. So I'm quite convinced today that this is a very important feature of deep learning, and we see it all the time. It's also, there's something I'm going to elaborate on Friday, which has to do with this interesting relationship between deep learning and between mutual information and computational complexity, but that's something I want to skip now. So essentially, one of our main results, as I said, is this rethinking about learning theory. So I know that I'm running too slow. This is the type of generalization bounds, the PAC bounds, which are essentially given in terms of the generalization error, what is the error out of sample, bounded by the log of the cardinality of my hypothesis class, divided by the number of examples. As I said, for large errors, for large problems, the confidence, this 1 over delta, is completely negligible. You can forget about it. Because the probability of getting a non-typical sample is 0 when you talk about millions of images or millions of objects. Now, the problem is with this log cardinality of the hypothesis class. In general, in learning theory, we either assume that this is finite and then we get a cardinality bound, okay? Or we assume that we can cover our hypothesis class, the function that I'm trying to learn, by a finite cover up to some approximation error epsilon. This is what we call an epsilon cover or an epsilon net or an epsilon grid of my hypothesis class. And usually we can learn classes for which this cardinality of the cover, h epsilon, as I write here, scales like 1 over epsilon to some power. And this power is usually used as the dimensionality of the class. So if you all know something about VC dimension is a special case of such dimensions. If you know about Hausdorff dimensions or other types of dimensions used in mathematics, it's precisely this type of definition of dimension. Now, what is nice about this is that if you plug this into the log here, you get that the main factor in this bound is d over m. So usually you don't generalize until the number of examples reach the dimension of the class. And once m is much larger than d, this epsilon is really bounded by 1, and you're happy. Okay, so this is why such bounds are so powerful and useful in general in learning theory. The problem, as I always say, this dimension is way too high for deep learning. It's order of the number of weights, more or less. It can be less than the number of weights, but you're using convolution neural networks, you're using all sorts of other tricks. This doesn't explain in any way the success of deep learning, because we are already working in cases where the dimension is 10 or 100 or 1,000 times higher than the number of examples in my data, which means that this is not the right theory. And actually a lot of people are actually working hard on expressivity results, which show us that deep neural network can express very complicated functions, where in fact it's only pushing this dimensionality higher. So I suggest a different type of bound, and this type of bound is deeply related to information theory. So if we could actually, instead of working with some sort of hypothesis class, what functions can be approximated by the network, think about how much I can actually reduce the complexity of the input. Now, this is not new. In learning theory, actually one of the classical old results is called k-nearest neighbors, for example. K-nearest neighbors tell us, look, you want to generalize, just learn from your neighborhood. If you are similar to your neighbors, then it's okay. And the k-nearest neighbor is actually not so bad. It's actually not worse than twice the base error or something like this. So k-nearest neighbor is an input compression or input approximation. It doesn't have to do anything with the class. There are other, much more sophisticated bounds which depends on the input. One of them is known as stability bounds. If my learning problem is not sensitive to noise in the input, then I know that I can generalize. If my function is bounded in terms of derivatives, for example, it's Lifshitz or something like this, with some bounded coefficients, then I'm also in good shape. If I'm band limited, for example, I don't need very high frequencies, then I can sample my problem. So sampling problems like the Nyquist sampling theorem, which twice the highest frequency or something like this, is again an input compression result. I don't need more than a certain finite number of samples of my input in order to approximate my function. So essentially what I'm saying, there's a general form of input compression results. Essentially, if I can cover my space of all possible images, all possible x's, by some cells which are homogeneous with respect to the label. So within each cell, I'm going to have essentially the same label, no matter what the class is. so some sort of continuity or some sort of topology of my input space, then I can take this cardinality bound from the worst possible case, which in the Boolean case is 2 to the cardinality of x, to something else, which is 2 to the cardinality of my partition or my cover. So if I can do this, then something quite surprisingly happens. Let me jump here. Something surprisingly happened, because essentially this cardinality bound is related to the mutual information that I have in my input, in my compression. So I'm sorry, I skipped something important here. So first of all, I want to homogenize my cells. I want them to be uniform with respect to the label. This is something which I can guarantee by maximizing the information on the label from those partitions. And this is essentially what is done through the gradient descent by essentially homogenizing these cells with respect to the label. The other part, so I actually argue that rigorously you can prove that minimizing the distortion, this very specific distortion, the KL distortion of the label within each of these classes, if I minimize this, I actually maximize the information about my output, and this indeed guarantees homogeneous partition. But the other part is how large are those partitions in terms of keeping them homogeneous. So this is what I call the compression bound. If I can cover my space with cells which are homogeneous with respect to the label, as few as possible reduce exponentially the number of functions from 2 to the x to the size of this partition. Let me show you what actually happens here. So first of all, I just want to remind you, what do we mean by typical patterns? So typicality is a very important notion in information theory. Again, I'm sure maybe all of you know that, but there are people out there who don't know that. So what do I mean by a typical image? Why can I actually use this notion? So imagine that an image has some model, something like a Markov random field, which means that the probability of each pixel being, let's say, white or black depends strongly on the pixels around it. So if I can actually write the probability of my patterns as some sort of a long product of conditional probabilities, and this is precisely the case with Markov random fields, with hidden Markov models for speech, for hidden Markov models for molecular biology, with almost all the Bayesian networks or the graphical models that we use in practice. These are all localized models where the pattern itself the probability of the pattern can be expressed as a product of many, many conditional distributions. Now, when this is true, this magic of information theory happens in the sense that the log of this probability get into a sum of independent variables and average, concentrates. And this is what we usually call the Shannon-Macmillan theorem. So the probability of having many, many variables like this, which are conditionally related, such that it can be written as a product of many terms, eventually approaching the limit of very large objects, a limit which is known as the entropy of the source, of entropy of this. This is the Shannon-Macmillan entropy. So this is a miracle in the sense that if this actually happens, and as I said, I mean, this is true for essentially all the patterns for which deep learning works. They are locally factorizable in some sense, in some very complicated sense. So if this is true, then something even more remarkable happens. Essentially, all the typical patterns have the same probability, which is 2 to the minus and the entropy. So it's not only that almost all the patterns become typical, but that all of them are equally probable. Now, if this is also true for each one of those partitions, so each one of those clusters or cells into which I actually divide my data is also typical. And I argue that for large problems, this is precisely the case. I mean, so you have patches of images, or you have pieces of speech, or you have some typical molecules in a very large protein or whatever it is, which are typical locally. Then even the condition probability of given each part is also exponential in the conditional entropy. So this is a very important, maybe the most important property of the information theoretic functions. This is also the key why they work for communication. But now I'm going to apply it to learning. So I'm going to replace those generalization bounds on the left with those compression bounds on the right. So remember again, I now think about typical inputs. So the size of X, the size of all the typical images, is precisely 2 to the entropy. And I suppress N here. I mean, N is eliminated. It should be here, but it's 2 to the entropy of the big variable. Because this is 1 over the probability of one typical object, which is exactly, they're all equally probable. So this is the number of objects, and the same is true for each one of those cells. So the average partition size is 2 to the conditional entropy. But now remember, I wanted to replace 2 to the S by 2 to the partition size, because this is going to simplify my input. And when I do, but the size of the partition is simply the size of X divided by the size of each of those covers. So it's 2 to the age X divided by 2 to the age X over T, which is precisely 2 to the mutual information between T and X. Okay, so that's very nice, because remember in my video, ITX is precisely what the network is working very hard to reduce. This is this compression phase. So this compression phase is exactly what minimizes the bound. So now I have a very interesting bound. I mean, the generalization error, the probability of making an error outside my set, which, as I said, depends only on the mutual information to the label, is bounded by 2 to the information, the compressed information of this partition, divided by the number of examples. So this is quite striking. If somehow the network managed to compress my input by k bits, it's exactly like multiplying the data size by 2 to the k. So 6 bits of compression of the input, as you saw in some of my images, is like 2 to the 6, more factor of 2 to the 6 more examples. So this is huge. This is exactly, I mean, this double exponent, because I have 2 to the information in my cardinality bound, is giving this compression ability a huge power in terms of generalization. By the way, you can show that this generalizes those stability bounds and robustness bounds which are known from the literature. Okay, so now the question is, what is actually the best compression that I can achieve in this plan of information about the input versus information about the output? And that's precisely where the information bottleneck comes into the game. So information bottleneck, as I said before, was an idea developed for speech and for thinking about extracting relevant information in general. It can be thought as a principal method for extracting minimal sufficient statistics. But since minimal sufficient statistics, for those of you who know something about it, are restricted to very special distribution, exponential forms, I wanted to relax it just slightly and ask, what is the most compressed representation of my input subject to some constraint on the information that I preserved on the output or on the parameter of distribution? And this gives us very simple, or not so simple, but actually simple-looking variational problem. Minimize the information about some representation, which I call here x hat, subject to a constraint on the variable that you put. What is nice about this is that this particular variational problem can be solved explicitly. And this is the solution. So this gives me a set of equations, which are actually very simple. You can think about them as clustering. I mean, the first one is how much I associate a pattern to a cluster. So this is like k-means, but instead of squaring the exponent, I have the KL divergence between the ability to predict the label from the pattern directly versus the ability to predict it from the compressed representation, or if you want, the centroid of this partition or cluster. And the other important equation is this red one, which is just the basic statistics or basic probability rule. I'm simply averaging over all my members of the cluster. This is just calculating the centroid of the cluster in k-means, if you want. So this is nothing but, looks very much like k-means. And indeed, it is some sort of k-means, but the space is the simplex of distribution over y. And of course, if you play iterations, you can solve it by iteration just as you solve k-means. And this is what we call it's known in information theory as then Arimoto-Blaut or Blaut-Arimoto algorithm, which essentially alternating projection between these 2 or 3 sets of distributions. What is nice to understand about it, that these equations put a bound, this black line, in the plane of information. So the more I compress the representation, the less I know about the output. OK, that's clear in general, because I lose information about the output. But this bound is a wall. This is an information theoretic bound. There are no machines. There's no way to go beyond this bound. OK, so this is what I call the optimal learning problem. So why is it optimal? Because you already saw, based on the bound that I just proved to you, that the trade-off between accuracy and sample complexity, or the number of samples, is completely determined by what is the highest point that you can reach with a certain compression. So compression reduces the number of examples, and putting it higher improves the generalization. So if I can't go beyond this black line, there are no machines that can do better than that. Now, if I can prove to you, and I'm trying to, that in the next 20 minutes, that neural networks actually achieve this bound, or very close to it, this will be a proof that deep neural networks using stochastic gradient descent are in some sense optimal learning machines. OK, that's a very bold statement, I know that. Notice that in general, of course, we don't know the joint distribution of x and y. If we know the joint distribution of x and y, we could solve the problem without just doing optimal base rule or something like this. We don't know it, we have a sample. Now that's the tricky part of the story. So if I have a finite sample, usually a very small sample, I mean, maybe 1 million objects, but it's a very tiny sample of all the possible images or something like this. OK? So then I have to estimate my information about the label from a sample. Now, the tricky part here is that if I have only a finite sample, what I really know about the label is not the black curve in this figure, but the red curve. And the red curve is a finite sample bound, which I'm not going to get into details right now. How is it proved? It's actually very simple. So when I have a lot of information, which means I don't compress much my data, which means I have a very fine partition of my data, then I have very few samples, maybe not enough samples to even fill this partition. So then my true information really drops very quickly. On the other hand, if I compress too much, I also don't have, of course, I compressed into 3 samples, clusters only. It's not complex enough to represent my function. So there is a maximum somewhere of this red curve. And this maximum here is precisely the best you can do with this particular sample size. Now, we know how to estimate also this red curve from the data, given some Greek sample. So essentially what I argue, so think about this green line here is some network. Okay, actually you saw that it looks more like this in general, but okay, this can be one of those networks. And eventually what stochastic gradient descent is doing, according to this theory, is pushing the last hidden layer to this point, which is the best you can do with this finite data. Okay, and if it's doing this, this is, as I said, this is the optimal machine, because both the black and the red curves are information theoretic bounds. It doesn't depend on the architecture. Okay, so it's actually, in general, we suffer from 2 types of losses in this case. One of them is the distance from perfect prediction to the black curve. By the way, I exaggerated here. Usually these curves are much closer to 1, but just for the illustration, I put it this is a very noisy rule. So this is what we call the compression loss. Actually, everything moves here, never mind. This is the compression loss, and this one is the finite sample loss. And in general, I have both of them. So I need to keep both the finite sample and the compression loss small. Now, let's look again at deep neural networks. So this is one of my favorite slides here. Essentially, what you see here are those trajectories in the information plane of the layers. But now the color from dark purple to yellow represent the number of epochs of the training. So this is 0 epochs, and this is 10,000 epochs. And what you see here is how the network started. So this is what you saw before. You see, in the initial condition, there was a very fast drop of the information. But then when you start to climb up, you see these nice trajectories, and you eventually converge to very high information. Now, this yellow line here, which is almost straight line here, is the information bottleneck bound, the finite sample information bottleneck bound for this network. That's what I argue. And indeed, when you train it with much fewer samples, you see, this is here on the left, it's 5%. This is 5% of the data. This is 45% of the data, and this is 80% of the data. You see that when you are undertrained, when there's not enough data, this compression phase is actually hurting you. It's taking you down. And eventually you converge to a line here, which is theoretically information theoretic bound, which depends on some trade-off between these black and red curves. So we know how to calculate. This is somewhere in between, and this is when you have enough data, you're well trained. So this is quite amazing. I mean, so how is it pushed to this bound, to this line? So this is, as I said, these are the information bottleneck bounds, and this is essentially the key matching that we did between deep learning and information bottleneck. I mean, there are two things which have nothing to do with each other originally. We just mapped the problem as some sort of stochastic approximation of this optimal compression.
Okay, just one small question. Do you estimate mutual information on training sample or on validation sample?
No, I estimate mutual information on the Y here with respect to the true desired input, label, I'm sorry. So this is what you call generalization error. Of course, this is not what you do in practice. I mean, one of the misconceptions that a lot of people had about this work, I'm not suggesting estimating mutual information for anything in practice. I'm just using this mutual information view in order to understand what's going on in the network. It's a very different type of questions. I mean, my reviewers were very crazy, angry about, because how can I measure mutual information for million parameters network? Of course, I cannot. But my argument is this is the same picture for very big networks as well, and it's telling me what's actually going on. So this is just like an X-ray of the image of the learning of the network in a way which I couldn't see before that. I mean, nobody could tell me what's actually going on with this layer. Where do they move to? By the way, notice that every one of the points in this plan is representing a lot of different networks because of what I told you before. I mean, so a different reshuffling of the weights, completely different networks can have exactly the same point in this plan. So this is a huge reduction of complexity, which I actually argue is the relevant reduction. So in order to understand what's actually going on here, I'm going to show you the same video again of the movement of the layers, but this time I'm going to show it with the training and test error. And what you see again, so that during this first phase, which they actually comes up and a little bit moving to the right, which means actually increasing the information about the layer, and the error goes down very quickly. And then with the training and the test error, which are very, very similar here, actually almost saturate. I mean, they go through this very fast knee, and eventually you see very slow improvement. But during this very slow improvement, the layers of the network still compress, which according to my bound, which means that even if the training error is essentially negligible, I mean, I see essentially just fluctuations of the gradients, as I'm going to show you, essentially just very small training error, the compression is still working, which means I'm still improving generalization. So this sounds like completely ridiculous to lots of machine learning people. I mean, how can you improve generalization when the training error is zero, or essentially zero? So what else is going there? Where do you get the information that allows you to generalize better? So of course, what happens is that the partition that is induced by the layers is actually getting coarser and coarser. I expand those cells without hurting the error, because the error is constraining this diffusion, which helps in generalization. Even 1 bit of compression is just like multiplying by 2 the number of examples here. So this is essentially the story. And in order to verify that, what we did is we looked at the gradients. And this is, again, one of my favorite slides here. It has some things that need to be modified. So this is my network. My network has this Eiffel Tower-like weights. The layers are 12, 10, 8, and so on. 6, 4, 2, 1. Okay? It's a very simple rule. This rule has actually 12-point spread on a sphere with some invariances which are interesting. I'm going to talk more about it on Friday. And And essentially, what you see here is the magnitude of the gradients per layer, per weight for every one of the layers. So each color is a different layer. Red is the lowest one, and so on. What you see is the mean of the gradient, and this is the standard deviation, or the fluctuations of the gradient. Now, this is something which we notice, and then we realize that other people have noticed it also, that the gradient descent, or the stochastic gradient in deep learning, really shifts from very clean gradients here, where you see the mean is much larger than the standard deviation, to suddenly somewhere, and if you notice, it's precisely 300 and something epochs, which is where those layers converge together, then start to move slowly to the left. So this is the phase transition that we see in the curve of the information plane, right and then left, and it precisely happens when the gradient shifts from what I call high signal-to-noise gradient, very clean gradient, to low signal-to-noise gradient. Notice this is a log-log scale. Yeah? So most of the epochs are actually spent in the low signal-to-noise gradient, which means the mean is much smaller than the standard deviation or the variance, which means that the gradients are very, very noisy. Okay? So we actually have two phases, completely distinct phases. In the large-scale network, by the way, this transition becomes sharper and sharper, which is precisely what to expect in statistical physics from very large systems. And so this transition looks gradual here. It's getting sharper and sharper when you talk about very, very large problems. And in this second phase, I'm essentially doing diffusion under the constraint of the training error. Now, okay, and this is the general picture. I mean, believe me, I don't have too much time to explain. This is MNIST. This is, by the way, something very recent that Ravid did. Ravid Zevo has done most of the work under this simulations. This is the CFAR 10. All the reviewers wanted to look at it. So it's very hard to estimate the mutual information here because it's large data, 32 by 32 pixels. It's still a small problem, but it's already 2 to the 32 square possible inputs. Actually, it's not 2 because it's colors and so on. This is really objects. That's using all sorts of tricks. We measure the mutual information using this parametric model, and you see essentially this is one network, not averaged at all, and you see essentially the same picture. I mean, first fast climb and then slow compression, or forgetting if you want. This is memorization, forgetting. It's happened for all there. This is, by the way, an interesting case, the one on the right here, which is that all the layers, all the hidden layers up to some point have exactly the same width. Only the last one is different, and it's smaller. And you see that essentially there is no loss of information in all the first layers, but the last layer has exactly the same type of trajectory. It first moves to the left, and then moves to the right and remembers the data, and then moves to the left. And when it moves to the left, all the hidden layers in between are moving. You see these yellow points here and here. This is where the layers essentially move. So they compress, despite the fact that they didn't lose any information. They don't have to lose information, but without this motion to the left of the layers, you don't get good generalization. Okay, so now I just want to give you the punchline of today's talk. First of all, what do we learn from that about the importance of the hidden layer? So the hidden layers, so of course we did this experiment. We took the same problem, trained it with 1 hidden layer, 2 hidden layers, 3 hidden layers, and so forth, up to 6 hidden layers. And then, of course, 6 hidden layers has a lot more parameters than 1 hidden layer. So in principle, you would expect that 6 hidden layers should work slower. Well, you get exactly the opposite. If you look at the color, so remember the color is the number of epochs. You see that it's dark blue, dark purple here at the beginning. So when it's yellow or red, it's already very high in terms of epochs. And you see that with 2 hidden layers, although in principle I can learn the function, I know I can learn the function, it takes essentially forever to get here to high information about the label, which means high generalization. It's already red and yellow here, and after 10,000 iterations, I still don't converge to very good, to perfect modeling. When I increase the number of layers, let's say if I move from 2 layers to 6 layers, I suddenly see that all is blue, all is dark purple. Okay? So if all is blue, it means that I get to very good representation very, very quickly. So how can we understand that? So essentially, my argument now relies on understanding stochastic processes and diffusion processes. So I know that now I lose another piece of my audience, but it's all right. So stochastic, again, something computer scientists don't learn enough about. So stochastic processes or something like diffusion, random walks, if you want, things that are moved by random noise. We know for 100 years, essentially, or more, how these things behave. So they essentially converge to what we call a Gibbs distribution in statistical physics, or maximum entropy distribution. So essentially, what happens here is that this slow convergence, it's slow, by the way. If I had a convex space, my convergence to the maximum entropy distribution is exponentially fast. But I don't have a convex space. I have a space which is very rough, and there are many dimensions, many directions in the weight space which are irrelevant, which means changing the weights in this direction doesn't change the error. Or the gradients is very small, or zero. Actually, it's not very small because I'm using a stochastic version of the gradient. So some images tell the gradient to move in this direction, because in this case, your face was with another person, but in another images, your face was a different background, you get a different direction. And these batches, those many batches of the gradients, is pushing the gradients in different directions at different times, and this creates a random walk, essentially in a flat space. And a random walk in a flat space behaves like diffusion without constraints, so the entropy or the compression, the entropy increase is very slow. It actually goes like logarithmic of the time, because the size of this Gaussian goes like square root of t, and the entropy is the log of the variance. Okay, so I have a log of the standard deviation. So I get a logarithmically slow convergence. So which means that if I need to do this compression with one big random walk on only one layer, I essentially going to spend forever, and that's exactly what happens with fewer than layers. But if I do it where all the layers push each other, because they're just like, a train with many engines. So essentially, I add noise to all the layers together by this stochastic gradient descent. So all of them are compressed in parallel. And because the compression is exponentially slow in time, in general in this case, when you divide it into many, many layers, you actually get an exponential boost in the time of convergence. So this is really, so essentially the relaxation time or the conversion to equilibrium of the stochastic gradient descent is explaining how those hidden layers really help you. And they help you computationally. Of course, they also help in terms of expressiveness. I don't deny that. But that's not the important factor here. So essentially what I know, and again, this slide may be a little bit too technical, I know that I have a stochastic gradient descent, which is some sort of Langevin equation, which is converging to a Gibbs distribution, which is exponential in the error. And then I can show you, actually in this slide, that this maximum entropy distribution of the weights conditioned on the examples, when I simply use Bayes' rule and invert it and then freeze the weights now after training, I keep them fixed, and then look what is the conditional distribution of x given the w's and the t's, I get a maximum entropy, which is an exponential distribution in the DKL, which was used in the training. But if you remember my bottleneck equations, this is precisely the equation of the encoder in the optimal compression. So it's nothing more than using the Gibbs distribution for the convergence of the random walk, and then use Bayes' rule in order to find the conditional distribution of the samples and each of the layers. So each of the layers is approaching an exponential form in the DKL, which is exactly what you actually use when you train neural networks in using cross entropy, as most of us do. And surprisingly, this compression of the random walk of the diffusion is actually pushing you to the information bottleneck bound. And indeed, that's what we see in our simulations. So what you see here is the blue line is the information bottleneck line, and the red are the location of the layers. And the spread is due to you do it over 100 layers on a very small problem. When the problem gets larger, those variances get smaller. So what you see that's convincingly, within the error bars very nicely, the layers indeed converge to this optimal bound of what I call the red line. Actually, it's the red-black line of this information bottleneck problem. So in that sense, I argue deep neural networks are very close to optimal learning machines. I know that.
Excuse me, better. What is this? This is
okay. So beta, I simply had no time. I promised to explain it more on Friday. But beta is this, and this is going to be online, so don't worry. Beta, when you look at this Gibbs distribution and this stochastic gradient descent, beta is the 1 over the variance of the noise. So beta is essentially, or one of the variance of the variance. So beta is essentially the 1 over the randomness. When you have large noise, the noise, if you remember, is determined by the mini batches. So when you have small mini batches, you have high noise. Large mini batches is low noise. But actually, it's not only that, because I look at the noise at every one of the layers. So since the noise is backpropagated through the layers, there's an added noise when you move deeper into the layers. Now, here you have to make a distinction between what I call the encoder noise and the decoder noise. So the encoder noise is accumulating the noise from the beginning up to the layer, and the decoder noise is what you use actually for the gradients of the error, goes from the end of the network backward. So if you actually make this distinction carefully enough, you really see that what you get here is what I call the encoder noise of the layer K, which is accumulated over the layers. And that's why in this matching to the bound, here you get the first layer has a very low noise because it's closer to the input. And the further you go across the layers, the encoder noise is getting larger. So that's why you actually get more noise, and therefore you converge to different points. And if you remember in the bottleneck formulation, of course you don't remember, beta was the Lagrange multiplier of the constraint of the information. So beta is directly related to the exponent of the error. So something quite funny happened here. Because you're using backpropagation, you backpropagate the gradient through the layers. And because you accumulate the noise from the higher layers, these two things play together somehow. And eventually, you converge to a maximum entropy on the information curve. OK? But there's more. And I have to finish. I promised to finish in 90 minutes. So the rest are more details about a very intriguing question, which really started my interest in this. So what you see here is a different picture. The color here, these are the layers, again, in the information plane. So this is the last hidden layer, this is the first hidden layer. But this is not as a function of the training error, the training epochs, but rather as a function of the number of samples after convergence. And what you see here is striking in the sense that you see that the layers converge in a very regular way. They always stop more or less in the same place depending on the problem. And that's peculiar. Why is this regularity? I mean, what actually stops the compression of a certain layer? So that's a riddle that I was thinking a lot about. And eventually, I think what essentially you have to think again about diffusion and stochastic gradient descent, and what can actually stop diffusion. Now, for this, you need more physics than I want to assume right now. But essentially, we know that diffusion can stop in very special places, like phase transitions, or like topology change in my space. Now, in this space of clustering of the information bottleneck, I mean, what is the topological change in my space? And then when clusters split or merge. OK, so this takes me really back to statistical physics. I know that what stops diffusion are what we call free energy barriers. Free energy barriers can be either an energy wall. I have to climb a wall. OK, this random walk through a wall will take a long time to climb a wall. But what also stops diffusion or random walk is entropy barrier. Entropy barrier, if you put a drunk here, it will take a long time for him to get out of the building, because you need to find all the doors and turn right in all the right places. A random walker will spend a long time, get stuck in such an entropy barrier. So essentially, if you think about those weights as doing a random walk, like a drunk has to move through a very complicated area, And this area becomes very complicated at this point, exactly where you have a phase transition or where you have a split of clusters. So essentially, in this case, the layers are going to get stuck. And so we can predict the location of the layers in some very specific places. Again, the location of each layer is determined by the nature of the problem, because those phase transitions can be calculated only from the joint distribution. So this is what I call the beginning of a theory of design of neural networks. You give me the problem, and I'll tell you how many layers are really good enough for good convergence, just from the analysis of the joint distribution. Of course, it's not a practical design problem, because I need to have the joint distribution of x and y to start with, but it's something to think about. Anyway, I want to just answer one little question before I stop, and that's it. This is just the caveat, the pudding of this dinner. One of the main results or consequences of this theory is that single neurons in these layers don't tell us much. It's really the whole layer. Because I can permute, not only permute, I can do any invertible transformation on the weights. It will give me exactly the same location in the plane. You will not see the difference. So starting with the different initial conditions or different order of the examples will end up with entirely different network, but in exactly the same location in the information plane. So one of the predictions which a lot of people are unhappy about is that single neurons, all these attempts to interpret single neurons, and this is a face cell, and this is a car cell, and this is an eye cell, or whatever, as long as you're talking about fully connected, if you don't constrain the architecture, fully connected deep neural networks, I think they're complete nonsense. But of course, if you have constraints on the architecture, you can see a lot of things. So sometimes you'll see a face cell, sometimes you'll see an eye cell, something else. It's more or less anecdotal. And the larger the problem, the less meaningful it will be. This is also, by the way, is a message for neuroscientists, for the brain. This is the reason why when we put an electrode in the cortex somewhere, it responds to essentially every signal. And you very rarely find a cell which responds to the face of someone. I mean, this is not, I don't believe those things actually, but if it happens, it's because of very specific architectural constraint. So here is the last movie. What happened to single neurons in this network? And essentially what you see, again, the same colors, but now I'm not looking at all the layer, but at every neuron of this layer in 100 repetitions. And what you see is, of course, that the lower layers, the red and green and yellow, carry very little information. Some neurons, are crazy. I mean, they jump all over. But eventually, all the layers converge to essentially the same information. I mean, up beyond a certain point. You see the neurons actually climb up. Okay, it stopped a little early, but never mind. So there's some problem with the movies here. But essentially, this is what happens. You see the lower layers really capture a lot of low information per neuron, and the higher layer, the information is much higher about the objects, and you need, therefore, much lower layers. Essentially, all the neurons tell you the same story. That's all. So this is my message for the end, and the rest will be for some advanced talk. So in sum, I argue that the information plan and this information theoretical analysis is, first of all, giving you a nice visualization. I mean, you actually see what happens in the network. And then it tells you a lot about this combination of information, generalization, and stochastic gradient descent. All those three components somehow play together beautifully, and you get really a much deeper understanding of the network. And of course, there are many, many further directions, like what happens in biology and how to improve the algorithms, but I'll be happy to answer questions.
Thank you very much.
Thank you very much.
So I guess there should be many questions. Right here, yes.
Oh, you actually got here.
So thank you for the very beautiful talk. It's a beautiful description of the behavior of the networks. We are a physicist both, so we can understand each other. Oh, sorry. Okay.
This is Ricardo Zucchino, by the way.
So my question is, can you prove, I mean, the kind of noise that you have in stochastic gradient is not the same kind of noise you would have in a lunch Venn dynamics. So my impression is that it's hard to prove that the stochastic gradient really converges to the Gibbs measure. I would rather believe that it converges to a stationary measure which is kind of subdominant and not really the Gibbs measure. What do you think about this?
Okay, so I'm not the only one who assumes that, first of all, the mini batches noise is more or less Gaussian, because you're talking about large problems, and if it's more or less Gaussian, then it's not such a bad assumption to assume that converging to maximum entropy or Gibbs measure. But Tommy Poggio, for example, is saying that, and many others. You're absolutely right. I mean, we don't have any direct evidence, but I have an indirect evidence. I mean, the fact that Bayes' rule on the Gibbs measure actually gives me the information bottleneck curve, and this is what I see, at least in these small problems. I don't know. It's not the proof, of course. So you may be right that in general, this Gibbs, the invariant measure is crazy because this noise is not Gaussian, and you can't use this nice asymptotic convergence of the Fokker-Planck equation. But this is what I know and assume, and it seems to be consistent with what we see in these small experiments. If you have other evidence, I'll be happy to see it.
Thank you. Yes, there are a number of people.
So, when training a deep network in practice, there is a well-known problem that basically gradient saturates. So,
I'm sorry, I didn't understand the word.
When one is training a very deep neural network in practice, it often happens that gradient saturates, and if nothing special is done about that, basically deep layers are not trained at all. So, contrary to this, like common observations, your analysis shows that the deeper the better. Do you in some way observe like saturation?
Very good question. So first of all, I don't know what you mean by deep. I argue, and I think this is said by many other people, that the last layers, I mean, closer to the input, closer to the output, are trained more than the first layers in some sense. And you're absolutely correct that the first layers can be almost universal. I mean, so if, for example, there is a topology in my problem, which means that I can actually compress the images, let's say, such that even I don't know what they're trying to label, if they're similar enough, the label is going to be the same. So it doesn't matter if there are cats or dogs or people or cars there. Similar images will get similar labels. And of course, this can be done either by exploiting symmetry, as we do, for example, in convolution neural networks. So symmetry is a very important feature of deep learning, I believe. And actually, in my next talk, I'll talk a lot more about symmetry and then how in symmetric cases we can actually predict the position of the layers very precisely. But so for example, convolution neural networks of all the sorts that are used all there are essentially exploiting symmetry, like translation invariance, rotation invariance, and whatever. Now, in those cases, you can actually cluster the hidden layers without seeing one label. It's a completely unsupervised clustering. And indeed, if you can do this, I mean, if you have additional information about the connection, the topology, you know that trajectories of this symmetry group or things like this keep the label invariant, then you don't need any data. You can immediately compress the representation simply by merging together all the groups which are related to each other through a transformation or are close enough or just noisy versions of each other and so on. So all these things are perfectly true. And what we see here, that indeed the lower layers don't compress all the way. I mean, they keep a lot of residual information about the input. And I actually argue that that's very good because then I can use the same lower layers for different problems. And I can do learning transfer. So for example, take any object recognition network, one which was trained, I don't know, on cars, and then take the first few layers and train only the higher layers to recognize faces, and this will work probably pretty well. Because essentially the lower layers learn the invariance and a few other very general things. So I don't know if this is a direct answer to your question, but of course this particular theoretical metaphor or structure allows me now to take those layers with high symmetry at the beginning and lower symmetry. Actually, the symmetry is growing up, but become more and more specific. There's a very nice correspondence between this type of structure and what we see in physics, since I see there are physicists here. I mean, for example, we can take a Hamiltonian, which is made out of Casimirs of a chain of groups, so just like as we do in nuclear physics or in molecular physics, and essentially see how the symmetry is extended when I go further across the layers, and you can get very beautiful correspondence between deep layers and the energy levels of some Hamiltonian system. It's completely mind-boggling how similar it is. But for most of you who don't know what I'm talking about, essentially this is just as you said. I mean, you can train the higher layers. They do a lot more work and a lot more compression for improving generalization than the lower layers. But I'm certainly not saying that you should go to the limit of infinite number of layers. There's a cost to that. I showed you that if compressed more. First of all, this is an asymptotic result. I mean, I get this very slow convergence by diffusion only when you are really deep into diffusion. So if you do a lot of small layers, you are not yet in this regime for each layer. So obviously you're going to pay very high cost on adding many layers computationally, and you're not going to gain much because the asymptotic convergence to the Gibbs distribution is not going to begin to show up. So there's some sort of trade-off. I don't know what it is yet, but clearly you shouldn't take infinite number of hidden layers. I mean, that's, yeah.
Okay.
Okay. Thank you very much for your brilliant talk. So my question is about transfer learning. Doesn't it mean that we need to perform some kind of early stopping if we would like to keep more information in our representations about the inputs? Because this is the information we would need when we perform transfer learning. Not information about these particular outputs, but about the inputs.
About some
So
general features of the inputs.
Yep. So is it a reasonable strategy to perform early stopping before we start squeezing the information about inputs?
Yeah, so early stopping, the best I can tell you from what we did about early stopping was in this figure where I showed you the layers. So here you see when you don't have enough data, you see that this compression is actually hurting you. And of course, you understand why, because you expand the partition, but you don't have enough samples, enough labels to know that it's actually homogeneous or pure with respect to the labels. So you expand the partition on the training data, and you get very noisy partition on the real data. Okay, but this is not exactly, by the way, overfitting. I mean, it looks very much like overfitting, but I'm actually simplifying the model, but I'm simplifying the model in the wrong way. So that's, of course, here, and let's say that this is really the typical case in many, many problems that you don't have enough examples. Here, early stopping will help you, because you are going to get more information before the compression, before all of the compression. Remember, this is a very toy example. This is 12 inputs and 6 hidden layers. We see, as I said, I mean, we see the same problem, the larger, again and again, actually, in an even more robust way, the same picture when we increase the size of the network, but of course the numeric becomes much harder, because estimating those information values is essentially here we just count after binning the neurons. I mean, discretizing the neurons actually helping a lot, but so this is for Ricardo again. I mean, I really believe that there you don't have to do this. You can calculate analytically, and you can do many other things.
Tali, here we start losing information both about inputs and outputs.
Yeah.
In case of large data sets, we're not losing information about outputs, just about inputs. So my question was about the information of our representations and the inputs, because this is the information we would need when we switch to another problem, not information between representations and outputs. And we are losing the information between representation and inputs, even in case of large data sets.
That's right.
So should we do early stopping?
So if you want to do transfer learning,
Yep.
So again, I mean, you need to tell me what do you know about these two problems between which you want to transfer. I mean, if they are both object recognition, okay, so I can tell you the first flow here, take the first stage of this neural network, it's going to be more or less identical because just exploiting symmetries.
Uh-huh.
But if you're going to transfer from image recognition to protein folding, there's probably very different that you can transfer. So very little that you can, I don't know. I mean, so I don't think there's a general recipe here, but yes, indeed, I know that the lower layers are more general or less specific than the higher layers, and if you want to do transfer learning, retrain the higher layers. Yeah. That's a general recipe that should probably work. How much and how deep you need to retrain depends on the proximity of the two problems.
Right. And one minor question, haven't you tried your framework for the residual networks? When we have these skip connections, it seems that we will not lose information between inputs and representations, right?
Very, very good question. I got this question from several good people already after my talk in Berlin. So it's indeed, so those of you who don't know, I mean, so ResNets or all this, so they use another term, which is essentially what they call reconstruction error. Essentially allow them to reconstruct the previous layer from the next one. So they really seems like avoiding or not allowing me to compress in some sense. Yeah. But then when you actually look at those networks, so we looked at several cases where this actually happened. So indeed, at first it looks like a contradiction to what we are saying. But then you see that actually, so images, for example, that they have a lot of nice examples, several papers which show that this ResNets or this reconstruction error actually helps in generalization, but from the hidden layer, the deeper layers, you have a noisier reconstruction. I mean, it's just like a better compression of the image. But no, JPEG images, for example, which we all use all the time, are 100 or 1,000-fold compressed compared to the raw data. And they still give us a very nice impression of the full image. So you can compress without losing, you really exploit the redundancy and the symmetries in a much cleverer way than just brute force compression. And I believe that you still compress. So we're actually running right now experiments on things like this. Mm-hmm. So one of the things that we see there is that both the training error and generalization error go down. But the difference remains very similar with the ResNets and before the ResNets, which actually means that you fit the data better rather than, so the compression term, which is essentially the bound or the thing that really tells me how well I generalize, stays quite similar.
Works with the same.
Yeah, but that's a very good question. We still work on it.
More questions? Yeah.
Wow. So I didn't manage to exhaust you completely.
Hello. Thank you very much for this great talk. I have two questions. The first one probably will be quite naive, but it's from a practical view. So from a pragmatic point of view, we as research scientists, we often face in the practical problems the problem when we need to debug and improve our model. So we just tested our model on some trained test data, and it performs poorly. We need to debug and improve its performance. So for that kind of practical task, does a practitioner can it use your framework and this information field, information plots to debug and some kind of get some insights? What can he do with his model to improve the performance? And the second question is,
and that's hard enough, but yeah. Okay, you want another one? No. Okay, so let me just answer this, and then because
okay.
I'm not going to remember it. So the question is, what is the message for practitioners? I mean, I think this is actually a very bad question in general. I mean, that's one of the fallacies and problems of computer scientists. I mean, they think too much like engineers. I mean, so okay, in this case, I mean, this work was rejected from both ICML and NIPS because of questions like this. I mean, I didn't give them any new algorithm. Okay, so first of all, okay, it's not an algorithm; it's an insight and understanding of what's going on in the network. So I don't think I need to apologize for that. But on the other hand, of course, I have an engineering hat, and I also want to get better algorithms. So, but it's not in one step. Of course, first of all, it's very hard for large problems to calculate those mutual information values. But there are many, many proxies. I mean, you can use all sorts of good tricks to estimate something. I don't really need the mutual information. I need something which has some similarity, some asymptotic proximity to mutual information. There are pretty much out there several interesting proposals these days. I can recommend one very nice one, came from David Wolpert's this year about, he called it actually deep nonlinear information bottleneck, but actually he proposes there a very nice algorithm for approximating mutual information using pairwise distances between the inputs. And so this is something like the correlation dimension in a dynamical system or things like this. But it's, OK, so who cares if it's exactly mutual information? What you want to see is this general trend of first fitting and then compressing the representation. And this you can do with a lot of proxies. The question is it going to help you debugging your algorithm? I'm not sure. But it certainly is a good insight. I mean, OK, how much, if you are not compressing, if something is stopping your compression, and you can actually show it's not compressing, I think it's a fundamental problem is the problem. By the way, problems which are not compressible, which means that they are not stable to noise, or not, or cannot be, in some sense, are not, these are not the right problems for deep learning in general. I mean, so, and then again, I get a lot of questions from people on this type of problems. I mean, they're using deep learning for encryption, for I don't know, coding. So these are, in general, unless there is structure in the data that you can compress, I mean, there is some sort of redundancy there, the deep learning is not going to work for it. So I don't believe that you can use deep learning per se to break codes, but I may be found wrong, of course. But anyway, so regarding the better algorithm, we are, of course, one of the most intriguing aspects of this story is that at the convergence, there is a very nice connection between the encoder and the decoder, which is precisely those information bottleneck equations, which means that you should try to somehow exploit it and push the layers faster than stochastic gradient descent to these self-consistency equations. So that's an idea which we are playing with. I guess that others are playing with as well. So you can actually combine somehow this alternating projection algorithm, like EM of the encoder-decoder alternation with stochastic gradient descent. But since there's a very nice thing that comes out of this exponential slowing down of diffusion, if I can actually enhance it to be polynomial in general, then I could solve some very hard problems in much faster time than we know with other algorithms. So I actually suspect that there's something very fundamental about this slowing down. But of course, we are looking for better algorithms, yes. Now, your second question, you still want to ask it?
Thank you. Thank you very much. And the second one is, do you have some insights or explanations in the language of your framework about the effectiveness and importance of dropout or other regularization techniques for the performance of neural networks?
OK, so strictly speaking, we didn't study dropout. We studied convolution neural networks a little bit. All those tricks like L1 or L2 regularization or sparsification or dropouts or killing neurons or killing, I believe they help. I'm sure they help. I mean, I don't argue with it. I just don't think that this is the main factor in the generalization performance. I mean, but you know, we haven't done the experiments. I mean, essentially what they do is simplifying the expressivity. I mean, they're simplifying the hypothesis class. And in that sense, they reduce the dimensionality in the pack base, in the pack bounds. But they don't, I don't believe, I'm really convinced that in most of the large problems, the compression is much more important than the specification. Now, surprisingly, for the compression bound to work, those irrelevant directions in the weight space, I mean, the fact that in many dimensions the arrow doesn't change, is actually helping me in some funny sense to forget the irrelevant details. So when you start to sparsify the network, you actually slow down the diffusion or the compression. So there's clearly some sort of inconsistency between, let's say, dropout specification and things like this and my story. But, you know, it's a trade-off. I mean, somewhere in between they can do better than both. Yeah. Who knows? I was playing with fully connected networks. The most that we did was CNN, convolutional neural networks, for the CIFAR and MNIST data.
Thank you.
There's still a lot to be done, yeah?
Yes, there was one question, actually. A few questions ago.
Good evening. Thank you very much for your tremendous talk. The first of my questions has already been asked. So, considering you said that you began your career as a physicist, I suppose I can ask such a question. Did you ever consider the analogy between the process of learning a deep neural network and the process of coming to a thermodynamical equilibrium in a Fermi gas? For instance, equilibrium in a thermodynamical equilibrium between ions and in a crystal or so. And the second part is connected with this one. So far, theoretical physicists know intrinsic constraints on the length of the process of coming to thermodynamical distribution. Probably we could use this intuition in order to find out some constraints on some minimality constraints on the time of training a deep neural network. So you were speaking of finding some faster than gradient descent methods. Probably there also are some intrinsic constraints. That's all.
Yeah. Okay. So it's again a long and involved question, but. So essentially, I'm using physics all over the place. Yeah? I mean, it's just that it's not a naive analogy to thermodynamics or anything like this. I'm saying that large problems have this typical behavior, which is exactly the secret of both information theory and thermodynamics, or statistical mechanics, and that the noisy nature of stochastic gradient descent is pushing me to some sort of an equilibrium distribution. This is the Gibbs distribution on the width. I mean, this is, by the way, an assumption we made long time ago in the 80s and 90s when we wrote papers on the statistical mechanics of learning in 1 or 2 layers. It's exactly the same assumption. And then we actually compared it to simulations, and it seems to be a very good assumption there. So here, of course, this is a huge dimensional space. I don't think we have any direct evidence, I mean, measuring the distribution, that you are indeed in an equilibrium Gibbs distribution, just as you can do it for the molecules of the air in this room. But there's a lot of indirect, which means predictions of these distributions, which we can test and measure, and that's why we know we are more or less in equilibrium here. Now, again, I mean, this was a very general question. I mean, of course, the physics intuition coming from statistical mechanics and stochastic processes is essential for the story that I'm telling, but it's a different story. I mean, it's a different type of system and different types of limits applied. So again, I'm not sure I'm answering you, but physics is a good education, if this is your question.
I guess it was the last question, right? So thank you very much.
Thank you.
Yeah.
I don't know. I don't know what screen recording.